From the previous power flow equation, we got two components of the power generated by the synchronous machine. One is active component P, another one is reactive component Q. But when two alternators are connected in parallel, we will get some other power called as synchronizing power. Synchronizing power, which can be either active or reactive. So when it can be active, when it can be reactive, how this synchronizing power affects the in stabilizing the set of the both parallel connected. Two examples. We have taken an example of connecting two alternators in parallel. How the synchronizing power is causing the stable operation we are going to discuss now. Consider two alternators are connected in parallel. This is a simple circuit diagram. Now operating under no load condition. Okay, step by step we will try to understand this mathematically. So, E1, say, before having any disturbance occurs, synchronizing power will come into picture only when the external disturbance occurs. Otherwise, machines operate stably, provided the conditions are satisfied to connect them in parallel. When all things are stable, no need of synchronizing power or external or inherent parameters to come into picture and to act. So, when the disturbance occur, then what will happen? So, under no load condition, ideally when two alternators with equal voltage rating, say E1 and E2. Why E1 and E2 I mentioned? Machine 1 and machine 2. Initially ratings are same, causing currents, say same currents, because when the load is connected, then current will be flowed. Otherwise, no load, no current. So, with synchronous impedances ZS1 and ZS2 respectively for machines 1 and 2. If armature resistance are neglected, then they can be treated as ZS is equal to equivalent to XS, synchronous reactances. Then, this is the circuit diagram. If a disturbance occurred by means of change in the excitation of alternator 1, as we know the EMF equation, if excitation means field, resultant field or main field, if we change or say increase, even voltage will directly increase, say up to some other value. Initially let us take 400, now it is now increased to say some 10 volts or 20 volts, some other range, even E1 dash. Now what will happen? One is having different voltage connected in parallel with the other connected voltage source. Though load is not connected, no load, two different voltage sources are connected, then current starts flowing. Within this set, this current is now called circulating current. Circulating current, it is circulating between two machines itself, not to the load. Ideally, it should not happen. Now, this circulating current causes what? We are going to see. That circulating current tries to synchronize these two machines. Now, okay, scroll this. So, if excitation of machine 1 is increased, E1 is increased to E dash. Now, current starts flowing. Now, how this current behaves in phasor relationship with the E1? No load. We are considering ZS as purely equivalent to inductance, means reactance only. So, consider ZPF. So, inductive load, then current caused by this inductance, inductive reactance by E1 would lagging behind the E1 by 90 degrees. After understanding this statement, we can draw the phasor. We can draw the phasor diagram, right? We will see. So, the machine 1 will operate at ZPF lagging. Why? Machine 1 is causing circulating current to flow, right? Considering it is purely inductive, synchronous current now lagging behind the E1. Yes. When machine 1 operates at ZPF lagging, as we discussed just now previously, alternator is operating at ZPF lagging. What we concluded by that, armature reaction is ZPF lagging, we discussed it. current is causing armature flux. Now that armature flux is reacting, interacting with the main field flux, causing the armature reaction. That is due to load there. Though load is not connected here, current is still flowing, acting as causing the resultant flux, affecting as demagnetizing effect. Yes, that's the point I want to say. So it is for ZPF lagging. If it is leading, that is now we term it as synchronizing voltage, not synchronous voltage, a synchronizing, trying to synchronize, which is causing ISY, lagging behind this by 90 degrees. Effect of armature reaction is not purely inductive. For inductive load. Demagnetize. Yes, next. After this, now from the power equations, we derived this, right? Active power.
Why E2 is opposite to E1? Then E2 and E1.
To say E1 and E2, they should be equal in all manners, but there existing a difference. To show that E1 minus E2, that is nothing but E1 plus of minus E2. E1 plus of minus E2, right, should be 0, right? To mention that in phasorly, to get the difference ESY, we are...
The two synchronous machines have different field. That is why they have, the phasors are opposite. Otherwise, if they have same direction rotation...
No, two different alternators. Two different alternators are operating in parallel.
So what is the magnitude of synchronizing current?
That difference in that depends on how much excitation we are changing. That depends on the ESY. ISY, that is formula is there. E1 minus E2 divided by ZS1 plus ZS2. Or otherwise, if you take equal reactance machine, the difference in voltage is by 2xs. So here is the expression. So magnitude of this synchronizing current is given by simple KVL. Loading condition I will discuss. This is no load condition. During loading, how the armature currents will differ, that case is there, I will discuss now. So synchronizing current is now given as the magnitude is difference in voltage by the effective impedance, total impedance we can say. So now if you understand, previously sir has asked one question, what is the role of reactive power? So here comes the reactive power concept here. When two alternators are connected in parallel, one alternator excitation changes, say increase, then synchronizing current will come into picture. That is called circulating current. We are telling in terms of conceptually it is synchronizing current which is causing the synchronizing power in purely reactive form. Because E1 ISY cos 90, ideally we are casing ZPF line, cos 90 is 0, sin 90 will become 1, so that is now purely reactive in nature. Machine 1 and this is causing synchronizing power because disturbance is given at machine 1. Now entire synchronous power is in the form of reactive power in nature. Usually reactive power establishes flux, active power establishes torque. Active power establishes torque. No. Rotations are to be same. Both are identical machines initially. It has its own governing system. Flux E is equal to 4.44 phi F Kp Kd for these machines. Its flux arrangement
its number of what you say armature winding, its KP are separate, identical but separate, and second machines are separate. We are trying to connect these two alternators in parallel. Now we are observing, after connecting this, we are changing one alternator flux, its excitation we are changing. Field excitation, yes, we can say that field current, main field flux, okay, by any means. No, direction will not, prime mover directions are all. Field current just increasing or decreasing? Increasing or decreasing? Then magnitude it will directly affect. That electromagnetic torque produced by this synchronous generator inside the armature will be opposite in the, it is just like DC generator and DC motor. DC motor, we get a back EMF, motor we give the supply, and it will induce itself an EMF which is opposing to the supply, say that EB. EB is nothing but EG in case of DC generator, Z pi P N by 60A, that is both are ideally equal. Similarly, in case of generator, motoring action also take place. We give the prime mover input to the generator, but inside the machine, counterpart of that applied torque will get induced, what we call that. That is what electromagnetic torque. In motor, generator action takes place. In generator, motoring action takes place. There we call it as back EMF. Here we call it as counterpart torque. Counter torque. Prime mover, if we give his input, yes, we can apply that analogy. Yes, to get the system stable. Ultimately, systems should operate in equilibrium condition. Right. Again. Yes, demagnetizes machine 1. Whenever the machine is operating under this demagnetization effect, it will try to reduce the increased demagnetization means what? Earlier, one excitation, main field, we are increasing the field. We are increasing the field due to which E1 is increased. Due to which E1 is increased, current started. Current is now causing demagnetizing means what? Increasing effect should be dragged back. Demagnetizing. That means we are increasing by external disturbance, the synchronizing current now trying to decrease the overexcited machine. Demagnetizing effect is taking place automatically. Sir has raised one important point. Yes, it happens automatically, but one more addition I would like to include that statement is, now we increased, system is trying to decrease it back. Point is, can we decrease it? Will the system, the synchronizing current will decrease as much as we increased? Can anyone guess and give a yes?
E1 and E2 are there equal.
Correct. Those E1 and E2 are the same as what we initially counted. Means initial condition has we taken. Can they be same? E1 we have taken as 400. Say I increased it to 450. Because of the demagnetization, machine tries to get stable. So E1 and E2 must be equal. Will it come back to 400 again?
No.
Correct, exactly. Because this is called set voltage. Parallel operation requires the conditions to satisfy. Rated voltages must be same. Need not be 400 only. 400 our requirement, because V reference phasor we are fixing line voltage 230. System set when disturbance is occurring, the resultant equilibrium voltage will set at a new voltage. Definitely higher than the set voltage. So that machine set should operate first stably. Who is causing that new stabilization? Synchronous power. Getting, sir? Synchronous power. So synchronous power is making automatically to demagnetize the first machine and magnetize the second machine in order to have the set voltage constant at a new level. But we want our predefined voltage level. Then what should we do? Again you should decrease. Because disturbances happened, we should clear the disturbance. Fault happened, it does not automatically get rectified. We have to clear the fault. That means which disturbance occurred, okay, we got the result. Set voltage on the panel we are seeing greater than the rated. Okay, something happened, control panel, we do this, again excitation lesser to it. Then we do the control and operation management at the station. So this is one of the aspects I used to tell to students. We used to reduce the excitation. Next, this is effect of changing in excitation when constant mechanical power input. As I told, reactive power establishes flux. Excitation is nothing but flux. When this flux is changed, synchronizing power is now purely in the form of reactive power. That reactive power is only trying to balance now to get the new set of voltages. Now, that time I consider prime mover input of the alternators constant. Now, second case, I keep excitation is constant, prime mover inputs I vary. Sir, can I guess, can I have any guess from you that if prime mover input changes, what can change? Yes, which in turn may cause change in frequency. Change in frequency that eventually may differ in frequency differs in term E1 and E2. E1 and E2 must be constant. Now I am not changing excitation. Excitation is now quantitatively equal to E is equal to 4.44 or directly proportional to 5. 5 I am keeping constant. So E1 and E2 are now constant. But now I am changing prime mover input. When prime mover input I am changing, magnitudes are equal. But what can be changed now?
Frequency of machine 1 and machine 2.
Okay.
A new equilibrium frequency will be created.
That is okay. What is changing? E1 and E2 magnitudes are not changed, but then why new frequency has to set? What is
The angle power and
yes, exactly. Yeah, phase gets differed. Phase is now getting differed. We are getting the changing different. So that where is, okay, just starting. No, scroll it down. Scroll. Yes, here. This we understood, I think. The first case, when prime mover input is constant, flux is now changed. How it is remagnetizing the first machine, magnetizing the second machine, so that new set will become stable with increased voltage. Now, next case, effect of change in mechanical power input. Say if in case of thermal station, steam input we call this, or fuel input. Then what will change? Phase will change. Phase will change, then also current flows. Right, magnitude same, but phase is different. That means something is different. Voltage is different. Then also now current starts flowing under no load, which is trying to synchronize the machine set, both the incoming and existing. Now how will be that in nature? Now this time synchronizing current will be in what nature? We will see. As sir told, upon changing the prime mover input, if I keep constant, same speed, 1500, say 1500. Now if I change, say 1600, prime mover 1 I changed. Then what will happen? Yes, please, now go for it. Yes. Very good. Yes, sir. Yes, sir. Your conclusion is correct. Let me explain for other audience a little bit in an elaborative way. So, show that phasor diagram. Yes, see now. E1 earlier is E1 itself. Now also magnitude wise E1, but now they exist in a phase difference. So E1 and E2 are now in phase difference. Earlier is this phase. E1 plus E2 must be 0. It means by KVL minus E1, if you write two voltage sources in parallel, even in order to satisfy the KVL, what is the law? Minus E1 plus E2 is equal to 0. That is nothing but E1 is equal to E2. But now E1 is now phase. It is having phase relation. Now when E1 is shifted, now we have a resultant EMF. Resultant voltage phasor. That is nothing but synchronizing voltage, which is causing synchronizing current. That time, synchronizing current. Look at here. From that synchronizing current, now what is the power how this synchronizing current now? Synchronizing current phase relation. Synchronizing current now phase relation. When both machines are operating at no load, when mechanical input of one machine is changed, synchronizing current now with respect to active component. Under no load ZPF operation only, under no load mostly and ideally zero power factor. Now the synchronizing current is in phase with the E1 ideally. So angle between E1 and ISY synchronizing current is ideally 0. When ideally 0, what is active power expression is giving us? E1 into ISY synchronizing current into cos 0, nothing but E1 ISY. Synchronizing power is now purely active power. The power which is trying to synchronize means avoid the disturbance or settle due to the disturbance at a new constant values is now purely inactive in nature. P1 is equal to E1 SY. Q1 will become, now reactive power is 0. So synchronizing power can be both active power as well as reactive power, subject to the type of disturbance that we are creating or it is observing. Right, scroll up. As I discussed, these are the points to consider. Reactive power always tries to establish the flux. This is also called as magnetizing component. Magnetizing power. In case of induction machines, they are always under excited. They are always under excited. In case of transformers also, induction machines and transformers, we need magnetizing powers so that to establish the flux. Then only the other operations will get affected. Means we will get the, after the magnetizing power, then we will transfer the entire input power, say active power input, utilizable power input. So reactive power plays a major role here in parallel operation, right? And the magnitude is now similar. This time phasor difference. E1 minus E2 by total impedance, effective impedance, right? Yes, now this synchronizing power is now purely electromagnetic in the form of electromagnetic torque. This will act now in opposite. Something we are creating disturbance, system is trying to settle itself by counterparting it. Just as in case of demagnetizing effect there, now it tries to make the disturbance opposing. That means what? If you are increasing the prime mover input of alternator 1, this synchronizing power being fully in active form tries to counterpart. It means what? It will reduce the change. From 1500 to 1600 if I change, it will try to align with again 1500, but not completely again 1500, some other value above the 1500. One way it is decreasing the prime mover input. Other way, for other machine, it will try to increase. Now machine sets with new speed, means resulting in new frequency. Good observation. Now set frequency will be, but that is constant. We fix our standard as 50 hertz. Now set frequency may be 47. One numerical I would like to solve after this, then all concepts will be cleared. How load sharing occurs. For example, we are fixing 50 hertz to operate on no load. 600 megawatt load is there. One alternator 200 megawatts and another alternator say 400 megawatts. Each prime mover has its own governing characteristics, drooping characteristics, as we have studied this, right? That means no governor, no prime mover can give exact 50 hertz, however the load of it increases. Prime mover speed, which is causing the frequency to maintain constant, it cannot be constant throughout the any type of load. When the load is increasing, frequency falls, practically, drooping characteristics. When that is falling, say if you 200, 400, 600, machine 1 directly cannot share 200 and machine 2 directly cannot share 400. They share the load by satisfying certain criteria. What criteria? Upon understanding the cases, then we will see the practical example, how they actually share the loads just after this. Okay. So the magnetizing, synchronizing current magnitude is now phasor difference voltage by the total impedance or reactance. Start. This is the explanation. Just as in the case of previously, now active power will take into picture as in the form of synchronizing power by means of synchronizing torque. Okay, next. Here. Next. Here. Now loading conditions. Yes. On no load condition, alternator fails. No, it will stabilize. Synchronizing current always tries to stabilize. If that is not happening, that current start increasing. Yes, that will eventually circulate, that will become dead effect. Circulating current should be stable. ISY E1 minus E2 divided by XS. XS is constant because of the inductance value. Now ISY is defined by difference of voltage magnitudes. You are concerning about if the synchronization is not happening, difference is existing continuously. If this difference is existing continuously, it means what? It is keep on increasing. Circulating current is keep on increasing, that means machine 1 and machine 2 are deadly now shorted. Yes, by means of that cumulative, so that will eventually damage. That should be limited. That is why in this current is causing to stabilize. That is why synchronizing power associated with stability. We discussed it just in the previous discussion. Stability factor. Synchronizing coefficient we are defining. No. This is two standalone alternators connected in parallel. Infinite busbar I am coming for the next session. After this next example is infinite busbar. First I am considering no load, two alternators, on load, two alternators, infinite busbar alternators. Okay, now we are considering on load. So no load condition, two disturbances. Effect of changing in excitation, effect of changing in prime mover input. We got to know how synchronizing power now being act as a purely active power, reactive power and active power, trying to stabilize the system at new set values. Then on the load, when the load is connected, IA1 is drawn by the armature 1 of alternator 1, IA2 by the armature 2 of the alternator 2. Together they are delivering a load current as IA1 plus IA2. That depends on the load, how much load we are connecting and type of load also. Now what will happen? Ideally if we consider as in the previous case, E1 is equal to E2, 400 say, IA1, IA2 all are equal. Next, if disturbance happens, change in excitation, say, if excitation of machine 1 is increased E1 to E1 dash, then synchronizing power will come into picture, which is purely reactive power. Next, the synchronizing power now supports first machine and opposes the second machine, demagnetizing, in order to have the stabilizing effect. Next, first machine shares more reactive power. First machine shares more reactive power as per the load requirement. As per the load, they are not equal. See, all are equal. In case of all are equal, we must get IA1 is equal to IA2 in terms of load condition also. But when excitation is increasing, reactive power sharing is now deferred. That condition I am going to discuss. Yes, those all points I have written in my notes. So one after the other I am going to tell them. So machine 1 will deliver more reactive power. Load sharing is now coming to picture. How the machines are going to share the load. Machine 1 is sharing more reactive power. Machine 2 is sharing less reactive power. Yes. Effect of change in excitation causes only change in its reactive power sharing, but no change in its active power sharing since mechanical input is constant. Yes, if we draw the this power table, machine 1 and machine 2, reactive power is increasing for machine 1, power 2, reactive power is increasing for machine 1, power factor will decrease. Good observation. Power factor now is reducing for first machine. Second machine, power factor tries to increase. Yes. Next. Effect of changing in mechanical input. As we discussed now, when mechanical input is changing, it affects the speed, thereby frequency. From the set frequency, if we are fixing, now frequency is varying, how the load is being now shared. Effect of change in mechanical power, the statement what I have written is active power. Is in active power. Someone has to share active power more. It means, see, we have for an alternator, P plus JQ are fixed. P plus JQ, apparent power of an alternator is fixed, kVA rating of alternator fixed, but we are connecting it parallel and we are disturbing it. Suppose we are disturbing it now, one machine is supplying more than the existing, means what? It is overloaded. Correct. It is overloaded. One can be overloaded. Before the rating, okay, it is valid. If say below the rated values, we can load the machine, but beyond the capacity of the machine, we should take care of. Right? Machine should not be overloaded. That will cause heating and some other unwanted effects. To have that understanding while doing analysis, so by theoretical calculations, now we are finding how much is the load sharing between the alternators. For two examples we are considering now. Next. Yes. Similarly, when the mechanical input is changed for one machine under load, keeping the excitation constant. When excitation is constant, reactive power sharing is constant. kVA R1 is equal to kVA R2. Active power, say, increasing for the first machine. Here, second machine will eventually decrease, because if this is changed, this is also changing, machine will not, set will not become stable. There is no concept of synchronizing power if it doesn't help. So, armature current now also exists because it is the combination of active and reactive power. One is maintained constant and other one is increasing. Yes, armature currents also will vary. Now, power factor. When active power input of machine 1 is increasing, kVR is constant, kW is increasing, power factor is nothing but adjacent cos rate, kW by kVA. Apparent kW increasing means power factor will increase. First machine power factor will increase. Second machine power factor decrease on load. This is the condition on load. This is due to the purely active nature of synchronizing power under parallel operation of two alternators. Next. Keep it here. Active power can be controlled. Now we got a new set values. In order to reduce the voltage, we should change the excitation of machines, alternators. In order to change the prime mover inputs. We should change the prime mover. Mechanical power input power can be controlled by changing its what? Active power can be controlled by changing the mechanical input. Reactive power can be controlled by changing its excitation. That is one notable observation. Next, governors, machines 1 and machine 2 prime mover. Usually prime movers are turbines. In any power plant, turbines, we have different types of turbines, Pelton wheel turbine, Kaplan turbine, Francis turbine, different turbines. They have different load and speed characteristics, torque speed. Otherwise, what here we say load and frequency, since those are our standard terms. We set a frequency is fixed. But it varies, drooping constant. Just like in DC shunt motor, terminal voltage must be constant for any type of load. If you are increasing load, if you observe the out external characteristics, then what will happen? Terminal voltage will droop because of armature resistance and armature reactance stuff. Armature IA, right? EG minus IA RA is equal to V. So when IA is increasing, yes, definitely this drop is increasing, net voltage decreases. That is why we are having drooping characteristics. Similarly, in case of mechanical characteristics of turbines also, when the load is increasing on the alternator side, prime mover, governor out, this turbine output will also get affected. Considering the starting case, now since we are talking about the prime mover input changing, so we need to consider first this effect of varying the frequency with respect to load. Say for machine 1 it is X percentage for W1 wattage loading and Y percentage for machine 2. With these two different characteristics, these two are now operating. What will be the resultant frequency and what will be the sharing of these loads, sharing of the machines for a compound demand. Say machine 1 is W1, it is its rated or capability, W2 it is second machine's rating. Together how they are sharing the load, that we are going to see now. Next. This is the case I told just now in case of DC machines or okay. AC machines also we can give the explanation in that way. Okay, numericals. These are numerical. One numericals I would like to give as an example. This numerical, yes. Show the problem statement. Okay, I don't ask you to solve it, but anyway to verify the answers, okay, you can solve it. Two alternators are there. One is say 200 megawatt, another one is 400 megawatt. On no load, the frequency of both these alternators are at 50 hertz. In order to supply, and their drooping characteristics are given. For alternator 1 is 4%, means no load to full load, the frequency change of alternator is 4% of the initial rated value. That is the drooping characteristic meaning, 4% as well as 5% for other alternator, machine 2 from no load to full load. Then when these two are operating in parallel, how they share the load? 600, sir, it is given 200 and 400 of two alternators. Our assumption student will understand, he will get a naive conclusion that 200 is one alternator, 400 is another alternator, together they can share 600. What is rating of machine 1 share? 200. Share of machine 2, 400, but actually it is not. Why? Both are not operating at same frequency characteristics. 50 hertz is a cap we are keeping. One is having upon full load 4% droop, another one is having 5% droop. Now sharing is different. Sharing is different. How? First problem, what is the system frequency now will be? This is a gate question. First option it is given as 50. We think always in electrical system 50 Hz, 50 Hz. First option is 50 Hz. But it is not actually 50 Hz. We are going to derive this by first, what is the system frequency? Load shared by alternator 1 and alternator 2. What is the maximum load that can be shared by this system without overloading any machine? That is the third question. Okay, we will see this by means of a plot. Means starting. It's very simple analysis. Just by mathematical solution, we can come to the conclusion. Okay, no, scroll down. Yes, further. Yes. Set frequency 50. Machine 1 200 maximum load. Machine 2 400 given data. Upon full load, machine 1 droops from 50 to 4% of it. Say, machine 2 upon full load has a drooping characteristics from 50 to 5%, right? Now you are combining these two machines to share a common load. Common load must be shared. Common load P1 and P2, common load must be shared. So at what frequency? Now what is the new set frequency? We do not know. Say X%. This is X% for the combination. This is now looking at similar triangles from the mathematical geometry, similar triangles. P1 by 200, P1 by 200 is equal to X by 4 from this triangle. If you can say machine 1 triangle and machine 2 triangle, can we derive this conclusion? Just due to the symmetry of triangles. P1, this base by 200 is equal to second triangle. Similarity of sides of the triangles. Yes, we can do this common. See, x by 4, one equation. P2 by 400, P2 by 400, consider this triangle, 50, 400 megawatts side with common frequency base, right? P2 by 400 is equal to x by 5, right? X by 5, okay, two equations, two unknowns, we can find x and the other. X now we calculate as how much? 4.61. Resultant drooping is now settling at 4.61. System frequency, he is asking new set frequency. System, now when they are operating, at what frequency they will settle? Ideally, no load, what is the frequency to operate at? 50. Its new drooping is giving at what percentage? 4.61. Can you guess what would be the new frequency on full load? Right, full load means now on this new load sharing, at this load 600 load, P1 plus P2 load, what frequency now they are operating at? X percentage of 50 rated, correct, around 50 minus of this X percentage of 50, that will result 47 point, yes, some value, yes, just for confirmation, 47 points. This is the set frequency. At this frequency, now if you calculate P1 and P2, yes, we have maths here, right, equations, P1 and P2, yes, scroll up, we got X, set frequency is now 47 point, we got X value, yes, P1 is equal to now 230, P2 is now we are getting 368. What are the rated values, sir, that we discussed? P1 is 200, P2 is 400, but if you observe 600 megawatt, if you are connecting as to this set, P1 is now sharing more than its rated. Now this is overloading condition. Overloading condition. It is showing, means before connecting the load, naively we should calculate, no, this is overloading, should be avoided. We will do some other arrangement such that machines cannot be overloaded, can be underloaded or fully loaded. Third case, third problem, we calculated set frequency, we calculated load sharing. Now we will see at what maximum load these two machines together can operate without overloading any. Can you guess, sir, what could be the maximum constant value that we will take? Yes, scroll down first, previous this diagram. No, not this. No, upper one, previous. Yes, this here. I am telling third case, I want to operate this system without overloading any one of the machine. What maximum can I give now for machine 1 or machine 2? What can I keep as a maximum fix? If I keep 400 as maximum load, this will be overloaded. If I take 200, this is lesser than 400, I can operate this beyond 200. So what can I fix for share of one load? One machine share I can fix, right? Because we want to share, see, the question is at what maximum load these two machines can operate without overloading any of it. This is the question. So I am thinking whether to keep this as maximum because we want maximum, or this as maximum, or both maximum. 200 if I keep maximum, share 600. Now that is not 600, maximum load is not 600 because 600 if you are keeping, this is giving 230, overload. I do not want overload, but maximum load. So if I am fixing this 200, this is coming under 400, 200 is lesser than this. So this can share more now. One power I am fixing. Machine P1 share under the maximum load sharing operation, P1 is given 200, that is fixed. P2 share must be calculated and what maximum value that this set can deliver, that we should calculate. Upon fixing this 200, now we draw the new drooping characteristics here. New drooping characteristic is this. We are fixing this 200 now. Because machine 1 is can be fully loaded. Machine 2, P2, we do not know. It is full load characteristic. Upon 400 giving 5% is the droop. Right. Now P2 is unknown. Right. Now maths. P2 by P2, okay, this ratio by this ratio is equal to this ratio by 4, okay, 4% by 5%, yes. We can do that. Now P2 is equal to 320, yes. Fixing here, first alternator rating itself is the crucial part. We can teach students in this way. Otherwise, load sharing always they may get confused. Always that inertia strikes. 200, 400, 600 can be done. No. New frequency, new sharing without overloading. Fix one maximum value, another value will settle at this value. Okay. So now the connected maximum load that can be connected to this set of parallel alternators is one is 200, another one is 320, resulting in 520 only. Though alternators are individually capable of giving 200 and 400, we cannot load the combination equal to 600. If you do that, one machine will get overloaded. The maximum of this combination is up to limited 520 only. That's the conclusion. After this, the case of alternators connected with infinite bus bar in parallel condition. Do you? Then mesh, if you keep 400 as one, machine 1 already gets overloaded. So you need not to connect any load first. 400 itself is the overload. Always which is lower, you keep fixed that because that is falling under the second machine maximum value. Okay. Okay, do you require any break? Okay. Let us have a 5 minutes break and assemble here quickly again so that we will continue the parallel operation of alternator with infinite bus bar. Welcome. स्क्रॉल ऐसा करो, देखो ये पेज दो साइड है, पहले
अच्छा अच्छा, ये साइड भी है।
ये साइड आएगा, फिर ऊपर साइड आएगा, पहले स्क्रॉल करना, फिर डाउन करके फिर scroll।
हाँ ठीक है, वैसे ही कर रहा हूँ तो।
डबल साइड,
हाँ ऐसे करके
फिर इसके बीच जाएंगे, फिर इसके
हाँ।
बीच। So after the understanding of parallel operation of two individual alternators, we do the parallel connection after satisfying the necessary conditions required. Then if any disturbances occur, what happens, that we are discussing, right? In the due course, we understood how the load is being shared by two alternators for various major disturbances. One is change of excitation and another is by means of prime mover input change. We understood how the synchronizing power will affect and the load sharing happens. Now another case of connecting the alternators in parallel is with the infinite bus bar. This is usually in practice. After understanding the primary connections, now we are going to analyze how these alternators are now performing when they are connected to the infinite bus. As in the morning session, as we discussed, the infinite bus, it means say number of alternators say are infinite alternators are operating in parallel. Say for example, each alternator is having synchronous reactance Xs, say all are identical alternators. So each are having Xs same. Infinite alternators, what is the, when they are connected in parallel, what is the resultant reactance, otherwise impedance? Yes. 1 by Zs, otherwise 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. That is DC circuit analysis is saying us. Parallel connected resistances, impedances. When number of alternators are connected in parallel, this entire impedance is giving zero impedance, ideal conditions. That means it is neither being affected by any change in voltage, some amount of changing, not at the drastic level, some amount of frequency, whether you take it from the arrangement, say what do you call that, infinite bus bar, grid we say usually at larger level, okay, grid concept is different, it involves lot of other aspects also. So infinite bus bar, whether you take some amount of power from it or you give some amount of power to it, be it what power we will discuss now. Properties of the infinite bus bar will never change. That is the condition we are observing. Yes, sir. Yes. Yes. Have you read my notes already? Or you also followed the same textbook? I think my next ideology concepts are your already existing in your knowledge. The same points I am going to derive just under this. Just go through this. Yes, sir. It is same. It is, yes. That point is here. Just write it. Just scroll on next page here. No, yes. Infinite bus bar can be considered as an ideal voltage source with zero internal impedance, infinite mechanical inertia. That's what sir has identified before that. Yes, it is having infinite mechanical inertia. It means what? You change some prime mover input for your incoming alternator, it will not get affected. That means our ultimate purpose is to share the active power to the loads. Reactive power is now how it is being managed, we are going to see. Always, if you connect this our incoming alternator to the infinite bus bar, active power will be transferred, injected into the bus bar system, infinite system. Yes, first one. No. Active power is always from alternator to infinite bus. Now reactive power is being shared from alternator to infinite bus bar and from infinite bus bar to alternator. How? That we are going to see. Okay. Active power. Now we will see the reactive power from the power flow equations. Go for this. That reactive power definition is now given as V by Xs into E cos delta minus V. This we derived. We have this derivation from the per phase equivalent circuit model. Now, Q depends on, if V is constant, say delta is equal to constant. Delta means load angle. Ideally, for infinite bus bar, for this stiff in a mechanical inertia, if it is close to 0. When it is close to 0, say, now Q is directly proportional to E cos delta. E cos delta, if it is greater than V, that consider, how can we get, if it is 0, cos delta, say delta it is 0, cos delta is 1, now it is directly, reactive power is directly proportional to voltage, EMF generated. So if this is increasing, how can it increase? EMF. How can we get increased excitation? So, if we are increasing, if the machine is subjected to over excitation, E cos delta will be greater than V. And if E cos delta is less than V, that is subjected to under excitation. If E cos delta is equal to V, normal excitation. These three cases we are going to see now. After that, we will see the analysis when it is connected to this infinite bus bar, how the reactive power transfer happens. Next. Machine delivers, okay, first case, over excitation. If machine is operating, alternator, incoming alternator is operating under over excitation mode. If E cos delta is greater than V, Q value, E cos delta minus V, E cos delta is greater, what is net Q? E minus V, that is positive value. Positive means what? It is delivering reactive power to the infinite bus bar. It is delivering reactive power. When you increase the excitation. If E is increased, reactive power will come into picture. That reactive power will be shared from incoming alternator to the infinite bus bar. That is one case. Effect of armature reaction is demagnetizing. Yes, here also, just like in the previous case, armature reaction is now demagnetizing. It will try to demagnetize. But sharing of reactive power is now into the grid, into the infinite bus bar. It delivers. Reactive power is delivered. One notation we will follow. Delivering plus Q, taking minus Q. Magnitudes are same. Magnitudes are same. Next, under excitation, if E cos delta is lesser than V, delta, if we assume load angle is 0 towards 0, cos 0 almost 1, then Q is negative. Magnitude wise same. What is this negative is indicating? The machine is absorbing. Again, reactive power establishes flux. In order to have the constant magnetic field inside the alternator, as per our EMF equation, when you are subjecting excitation change, the resultant constant flux is maintained at constant value by exchanging the reactive power either into the infinite bus or taking from the infinite bus. During these changes, normal excitation Q is equal to 0. Normal excitation, no sharing of reactive power. Okay, after this fundamentals. Okay, next. Okay, as the sir asked previously, role of reactive power. I think this entire session is now discussing on reactive power importance only, right? Just as in the case here, in this case, to maintain the constant flux inside the machine, reactive power sharing is happening now. It is only due to reactive power this flux establishment is now happening, right? One numerical example I consider here. Okay, after this, next, this side. Okay, this is explanation of that role of reactive power only. We discussed this. Next, yes. Now alternator. Okay, a little higher. Go for okay. Alternator on infinite bus bar under no load condition. Under no load condition, delta being assumed 0. E is equal to V plus terminal voltage plus drop, neglecting armature resistance. Then Q is given by V by XS into E cos delta minus V. Okay, under normal excitation, E is equal to V. Under normal excitation, existing voltage and incoming voltages are equal. Is there any power flow? No. So, IA, when there is no voltage difference, first no current. When no current itself, then no concept of active or reactive power. Machine is called floating, under floating condition. Machine is in this case now called as floating. Okay. Next. Floating condition occurs only under no load condition for normal excitation. Under normal excitation, over excitation. Next, one condition, we are having three conditions, right? Under, over and equal. Normal excitation. Okay, for over excitation, okay, E cos delta is greater than V. Okay, taking delta as 0, we are assuming, everywhere I noted as assuming load angle is 0, but practically E at an angle delta exists. In the equivalent circuit, early equivalent circuit, if you observe, terminal voltage V at an angle 0 I consider, because that from where our analysis starts. Once the alternator is giving at reference voltage Vm sin omega t, it means at no phase, at 0, entire electrical engineering starts from there. Analysis power system and etc. circuit analysis and all transformations etc. and we start from there. Before that, we need to establish the system first. Supply should be available stably. For that, what is happening at the generator level, this is the analysis. So always I am mentioning load angle is now assumed 0. When E cos delta is greater than V under over exciting condition, see the phasor diagram, current drawn, over excitation, ZPF, lagging, armature current, lags behind the voltage. Yes, the resultant IA lags V by 90 degrees, machine operates at ZPF lagging. Now, effect of armature reaction is demagnetizing, correct. Next. Okay, here. Effect of, okay. Next. P is equal to VA IA cos phi. Phi means phase angle between V and I. 90 degrees, assume, ideal condition. So, VIA cos phi, VIA cos 90, 0. Active power is 0. Now, Q is equal to VIA sin phi. Sin 90, 1 VIA, entirely Q. It is now on no load, machine is operating at 0 power factor with pure reactive power delivered to the system. Next, under excitation, if this is the case, if the machine is acting in the condition of under excitation, it will receive the power, reactive power only from the infinite bus. Next. Now, because leading there, that is lagging, considering ZPF 90 degrees lag, now ZPF lead, here cos 90 active power 0, now it is VIA again, but this time it is negative, absorbing. One notation we are following, different textbooks, I think mostly they follow one notation, I am following as per circuit analysis subject textbook written by Alexander Sadiku, I am following that subject. As per that notation, I wrote these equations. If they follow some other notation, please, I request don't get confused, but delivering, absorbing. Please keep this in mind. Students may get confused. Different materials may have different notations, right? That is algebraic. Okay, next. Any doubts? Yes, next. Yes, some range of power factors are given here. Just for idea, I am showing this. Yes, first down. Down means go up. Under no load condition, operating power factor for alternator range, practical range is 0.1 to 0.2. Over excited condition, under excitation 0.1 to 0.2 is the range of values we consider for alternators, and synchronous motor is also in that way. No load 0.1, it is 86 degrees around, less than 90 degrees. Okay, next, scroll down. Okay, these are the different ranges for different machines, electrical alternator, synchronous motor, induction motor, transformer, operating voltage. Next. Okay. Just for understanding one question, an alternator floating on the bus bar. An alternator floating on the bus bar, if the excitation increases when it is floating, now if the excitation is increased, power factor is power factor. Increase in excitation is increasing, E cos delta greater than V, E cos delta greater than V. In that case, what we got? Lagging power factor. Ideally, ZPF. So that is ZPF lagging power factor. Ideally, ZPF. Okay. That is one understanding question. Now, effect of change in excitation on load condition. Okay. If now alternator is getting loaded, say alternator is now delivering load, then what will happen? Active power definition we have EV by XS sin delta. Since active power is constant, P is equal to VIA cos phi per phase, that is constant. Since mechanical power input is constant, I am taking as active power is maintained constant. Now, if VIA is equal to constant, V is constant, terminal voltage is constant, synchronous reactance is constant. When these two are constant, now P is directly proportional to E sin delta from that value, EV by XS sin delta. So what are now constants in that? V, XS are constant. Now P is equal to become constant. Now Q is equal to, we have V by XS, E V by XS, E cos delta minus V. Yes, scroll up. E V by XS, E cos delta minus V. Just after this is actually
Yes,
two way.
Okay.
After this.
Okay.
Yes.
Okay.
Yes. From here.
Yes.
Just a little yes, here. See, this is nothing but the initial phasor diagram, what we have seen for a salient pole, cylindrical rotor, right? If you are taking terminal voltage as a reference, for lagging power factor load, IA, armature current, lags behind the voltage phasor at some angle. If it is pure inductor at 90 degrees, it will lag. If it is RL combination, it is less than 90 degrees. So V IA is a lagging with a phase angle of phi. Then IA RA I am neglecting. Otherwise, you will get an IA RA in phase with I. IA XS impedance drop, together this drop with the phasor reference will give yes, impedance drop plus terminal voltage will give E, generated EMF. For one IA, this is the plot we know. Right, under this load condition, when P is equal to constant, for a different IA, say IA, now I am varying with different loads. What type of loads do we have, sir, in for general understanding in electrical engineering? Broadly, inductive load, resistive load and capacitive loads. So, inductive, lagging, purely we may not have, but combination. So, lagging load, unity power factor load and leading loads. It means current may lag behind the voltage or in phase with the voltage and lead the voltage. So, I am considering different cases for armature current. So, IA, IA1, IA2 and so on. Then, if you see which is constant from the previous explanation, if you see active power is constant. So, this component E sin delta is becoming constant. E and V are having no delta value. One is along the V and another is another component, quadrature component with this V. That quadrature, that is what, E cos delta and E sin delta. Trigonometrical observation. So, E sin delta now is maintained constant. Now, if you see this locus of phasors, the resultant plots for each value. Usually, if you plot one armature current, one plot, IA1 different plot, IA2, IA3 with this varying in nature. Slowly, I am trying to make you aware that from lagging power factor to leading power factor, how this is varying, I am just trying to show. So, combining all these plots will give us the locus. From this we can plot a curve called V or inverted V curves for synchronous machines. Provided if we understand for generator, now we can simply do analogous analysis for the synchronous motors also. We do analysis for synchronous motors usually. Now, if you observe, during this resultant IA, IA1 and IA2, three cases, okay, go down a little. So, this is the plot we observe. So, always keeping active power constant, how reactive power is now varying, okay, next. Okay. This is again, for my understanding, I used to keep at the spot where and then required, I used to write the same notations again. Again, P is equal to EV by XS, sine delta, constant, active power component, Q, reactive power component, E cos delta, reactive power component. When E changes, delta also changes, though no excitation angle from E3 to E1. Okay, then we derive, we now plot the actual curve between, right, yes, between, yes, excitation and armature current, also power factor. With that locus diagram, phasor diagram, if we plot the curves of armature current with respect to field current and power factor with respect to field current, nothing but excitation. We have three modes of excitation considering, right? Then the plot will result in shape of V and as well as inverted V. So in order to make the student understanding, right from power angle, this power equations, we can directly derive when it is connected with the three modes of excitation, we can draw the V and inverted V curves. Simple way he can draw on his own by understanding. Otherwise, V and inverted V, under excitation, lower excitation, normal, it may cause confusion. Right. One plot if you draw, other plot will automatically result as the other. V, if it is known, inverted V is inherently can be drawn. This is one case, on load case. Right, next. Next, wait. One example happened. Next, scroll up. Next. Another. Next page. Slowly. Slowly. Wait.
The next page.
Now, mechanical power input change. If excitation is kept constant, second case, if excitation is kept constant and mechanical power input changes. So, we have excitation constant P, EV by XS sin delta. Now, V and XS are constant because we are operating it parallel. Right now, when V, XS and E are constant, then P is now directly proportional to sin delta. We are now varying delta. When the mechanical input is changed, this is the condition. Next, as the mechanical power input increases, P prime mover mechanical input increases. When the load is increasing, active power increases. Active power increases, it means sin delta increases. Sin delta increasing, it means delta is increasing up to the 0 to 90. Because stable operation, delta should be operated within stable region as we discussed, that is around 45, 30 to 40, 45 is the range we maintain. So during that region it increases. Next, yes. Now if we observe the phasor plot in this condition, same earlier we made reactive power constant, now active power we are, earlier active power mechanical input we made constant and observe the different phasors for different armature currents. Now we are drawing the phasors keeping excitation constant and prime mover inputs are varying. Then the plots from quickly can we have a guess sir what region at this side? IA when it is in this IA, this is V. What region means what type of load? Inductive load, lagging power factor region. When it is aligning with V, resistive load, unity power factor, beyond leading capacitive load, leading power factor region. then those phasors will result a locus of E. Ultimately, E we are going to observe. It will follow this track, right? That is the observation. Next. Yes. This is how we plot V and inverted V curves of synchronous generators. Provided this understanding is clear, we can do the analogy same for the synchronous motors as well. That part will be discussed by other experts from tomorrow onwards. Okay. Any doubts, sir, up to this? Okay. We will have some experimental laboratory sessions also to discuss the experiments as per this new syllabus. I think earlier syllabus and this new syllabus experimental list has not been changed. I think syllabus is same. The number of experiments and the experiments list also. Anyway, that we are going to discuss. Associate. See, how to find the ZPF method, voltage regulation by ZPF method, MMF method, EMF method. So, in order to make students aware, right, connection diagrams. Briefly, we in the laboratory session, how to deal. Students, how they do, they will come with a record, with a circuit diagram drawn. If we ask them to connect the circuit with the experimental connections, they will see the circuit and connect. Then, what is the problem? If any circuital mistake, ammeter, say if it is DC connection plus or minus, they simply can make a mistake, minus to plus, they will come to us. Right. Practical session. Practical session while we are asking them to connect. So there is a method of understanding without having the circuit diagram drawn on the paper and seeing every time how to connect them, how to make students connect them automatically, so that after connecting everything, once you look at this arrangement, that will look like a mess, complete mess. There is no proper like VLSI design, so proper understanding is not possible. That is how we do at NIT, our research laboratory, so much of messy arrangement, but each and every connection has its own importance and observation. We need to take care of that. So that is the method how to make them understanding without looking at the circuit diagram. Actually, keep the circuit in mind, they will draw themselves and they will see, and finally we as a faculty, we go there and we see positive terminal is connected to what side, MI or MC, which meter is connected, voltmeter, whether it is connected across or in series, per phase. Okay, if you are connecting this no load test and block otherwise short circuit test for alternators, we will see whether the terminals are open, voltage is connected line to line. So this should come with a flow. That experimental analysis we are going to see based on this understanding. Till now, theoretical discussions are over. So experimental part we will see in the experimental sessions. Okay. Any doubts within my knowledge? If you pose, then I would try to. Yeah. Yes, sir. I have this. Now, are you asking the PP this written material or? Yes, sir. Yes. It is my written notes only. I'll share this because after collecting multiple sources from different textbooks and different explanations, then very back, I passed out the BTech from 2007 to 11. So during my GATE preparation, I made these notes. So I'll share this anyway. I have this. I'll share this. Apart from this, any questions are welcome. Achha, is it available? Okay. Okay. Let us take a break. Please have the drink. I think we can wind up today's session. By now. Have you all signed the attendance sheet? It is required. Please make it. And tomorrow we will meet again for the next session. Tomorrow session is 3 days induction. I think 20. Tomorrow 21. Three-phase induction motors, probably. Tomorrow afternoon, I am going to take laboratory experimental sessions. We have a concept called virtual laboratories here. Also, okay, people of IIT departments, so they made some simulatory explanations of laboratory experiments. We will see what are the possibilities. Done, yes, can be simulated. How they are providing, let us get a familiar by those demonstrations in tomorrow's practical session. Tomorrow morning it is, I think I have shared you this schedule, three-phase induction motors. Already shared, three-phase induction motors. Tomorrow morning, 10:30 a.m. 21st February.